Thank you the organizers for inviting me to give this talk. My plan is to talk about, actually combine a little bit the data, the progress in the data and the theory, and on the theory side in large-scale structure of the universe. So I'll be talking, I'll start actually with some data, then I'll switch on to theory. I'll tell you a little bit about how the theoretical progress is being made, what are the challenges and stuff like that, and then I'll tell you about the data again and what the future challenges are both on the theory side and on the data side. All right, so first of all, let me start with the part which is very easy, where the theory is under good control, which is just homogeneous universe. On very large scales, we can think of universe as being homogeneous, and we can do things like redshift distance relation. This is what Hubble published, long time ago, and nowadays we have come a long way from that. This is a redshift distance relation where we measure the distance using the supernovae, which were thought to be standard candles, and we do the redshift, and so we get diagrams like that. And of course, as you probably all know, based on this kind of measurements, dark energy has been discovered, and the Nobel Prize has been given for that. So there's another way to do this diagram, which is not using supernovae, but using baryonic acoustic oscillations, and I'll talk about that in a second. But let me first, where do we go beyond the homogeneous universe? We first start to do linear perturbation theory. Linear perturbation theory for dark matter, for cold dark matter, for example, is very simple. You write down the action, you write down the equations of motion, just usually Newton's law equations on small scales, and then on large scales they have to be supplemented with some GR effects. We take moments, we write down basically phase space distribution, we take moments, and this leads to the usual Vlasov equation, that then if one takes the moments of that, one gets the usual continuity equation, relating velocity and density, for example, then Euler equation, which is essentially just Newton's law, and so on. And of course, this has to be supplemented by the Poisson's equation. So this, again, this is the Newtonian description. Then if you want to do the GR description, then we have to add some more terms here. So, and then what do? We linearize these equations. There are second order terms here, and so we linearize them, and we get the usual linear equations, which then lead to the standard growth of perturbations in an expanding universe. It turns out the growth of perturbations is given by this linear growth solution, which is essentially a power law, more or less, in terms of the expansion rate of the universe. And so, for Einstein de Sitter universe, it's particularly simple. It grows like this. And at late times, when dark energy dominates, then it falls below this rate. It grows less rapidly. In fact, it stops growing. So that's the linear theory. On large scales, on scales comparable to the Hubble scale, we have to supplement this with the GR. And then for other components, not cold dark matter, but for other fluids, for example, baryons is another fluid, we have to supplement this equation also by the scattering term between photons and baryons. And then for photons and neutrinos, it turns out fluid description is not good enough. We have to do the Boltzmann description, again, taking this phase-space distribution, but taking more moments. In fact, it turns out to be an infinite hierarchy in that case. We supplement this with Einstein's equations, which are just basically Poisson's equation, but applied to large scales as well. Plug into the Boltzmann codes, and the results are the well-known CMB anisotropies on linear scales, which have been proven really successful. So that's a success story of a large-scale structure and cosmology. One example is these baryonic acoustic oscillations. There was a movie, but I transferred this now, so I'm not going to show you the movie here. But basically, the idea is that photons and baryons are tightly coupled. They propagate waves out of initial overdensity, and these waves stall when a recombination happens. That's typically roughly at a distance of 150 megaparsecs. And that's a typical scale that we can measure in the data. In the CMB has been measured. You have probably seen those CMB power spectra. But it turns out you can measure it also in galaxy clustering. It turns out this is a standard ruler. This baryonic acoustic oscillation scale is a standard ruler because we have measured its physical scale using CMB. And then we can determine this standard ruler. We can measure it up in the sky in the galaxy distribution. Both in the transverse direction, we can measure it, where it's essentially telling us the angular diameter distance to the galaxies, and in the radial direction, where we measure the redshifts, and that's essentially telling us the Hubble parameter, if we know the redshifts. All right, so we can essentially measure two numbers out of this as a function of redshift. as a function of redshift of the galaxies. So this has been really successful in recent years, especially due to the Sloan Digital Sky Survey, which measures galaxies both at low redshift. This would be redshift less than 1, in fact, more like less than 0.7 redshift. These are so-called luminous red galaxies that have been used for this purpose. But there's also a lot of quasars with their own spectra, where we measure the so-called Lyman alpha forest, and we can also measure the same information out of this. So this BOSS survey is on 10,000 square degrees, 1.5 million galaxy redshifts, about 150,000 quasar redshifts. And the results are shown here, for example, for this baryonic acoustic oscillation. I'm showing this correlation function, for example. You see a bump here, roughly at 100 H inverse megaparsecs. In the power spectrum, it comes out even more nicely once you filtered out the broadband power, and it looks like this. Really nice oscillations. Now, if you just look at the distribution of galaxies in the sky, you wouldn't really see anything, right? You don't really see a circle by your eyes here, but when you do the correlation function or power spectrum, then this comes out very nicely. So you can also do this with this Lyman alpha forest survey using this 150,000 quasars, and there's a bump there as well. All right. In fact, there's a bump there both in the auto correlation of Lyman alpha forest and also in the cross correlation between Lyman alpha forest and quasars. There's a hint of a bump, but actually, nevertheless, this actually turns out to have quite a lot of information. So I can now do the Hubble diagram, the one I've shown you before for the redshift distance relation for supernovae. I can also do this for these baryonic acoustic oscillations. And here is shown, there are several different distances that one can define, as I mentioned before, right? One is in the Hubble direction, in the radial direction, one is in the transit direction, and one is the kind of averaged. And this is, a nice scaling and these are the theoretical lines for lambda CDM model. You can see the data are fit pretty well with lambda CDM, except for maybe some discrepancies at high redshift, which we still need to understand better, but they're only to sigma level. You'll notice that we can actually do this all the way down to low redshifts, and that, in fact, there's something which has recently emerged as the best way of measuring Hubble constant, which is we can combine these supernovae with these baryonic acoustic oscillations to so-called inverse distance ladder. We can measure basically the same, we can calibrate the supernovae. Supernovae, what are supernovae? They are standard candles, we think, but we don't know their intrinsic absolute luminosity. So we cannot determine the Hubble constant from the supernovae. We just know that they're standard candles, but we don't know how bright they are really intrinsically. But we can actually calibrate the brightness of supernovae using the baryonic acoustic oscillations if we do this at the same redshift. For example, we can do this at redshift 0.55 using this BOSS survey. These are the supernovae. The black points are supernovae. The blue point is the BAO. The two have to be calibrated, have to give the same information because they're measuring the same number as redshift 0.55, and then we can use supernovae to extrapolate this down to redshift 0. In this way, we actually get a Hubble constant essentially free of any assumptions. And the number that comes out to is about 67 plus or minus 1. This is, I think, very important because the value of the Hubble parameter has been all over the place for decades, basically ever since the Hubble has measured a number which was 500, then it was slowly coming down. There were long debates for many decades between people favoring 50 and people favoring 100. And now we think we know it to about 1.5% or so. Okay, so this is how much we can get from linear theory, just from so-called from the classical tests of cosmology. So linear theory, we think, this is a power spectrum of the density perturbations. We think linear theory works on very large scales, k less than 0.1 or so. K is the wave vector. 1 over k is lambda, it's 10 megaparsecs, so on scales larger than 10 megaparsecs, we think linear theory works well. And then on small scales, we think it's very nonlinear, and we have to go beyond linear theory. So how far can we go, and what can we do to go beyond linear theory? So let me now move on to beyond linear theory. So what do? We have perturbation theory. And there are actually several versions of perturbation theory. Let me first describe the standard perturbation theory, because it's simplest to understand. I've shown you already before that there are two terms that are nonlinear, but they're nonlinear in quadratic way, delta times v. That's in the continuity equation, and then this is v grad v in the Euler's equation. we can basically, since these are just quadratic terms, we can write them down in terms of the couplings of the second order fields. All right, and we can basically collect all the linear terms on the left-hand side, all the nonlinear terms on the right-hand side, but they are just quadratic. And we can therefore just write down a hierarchy and ansatz like this, and solve for this ansatz using, and we find these so-called kernels, recursive kernels, which solve for this equation. Okay, so if we want to compute the power spectrum, we have to do perturbation theory, and it has to be a loop diagrams that one has to solve. You know, so there's a 2-2 loop diagram and 1-3 loop diagram. So third order cross-correlated with the first order, and the second order autocorrelated with itself. And basically, you can go through the algebra, you get the expressions that solve for this. And you can go to higher loops as well. Okay, so in principle, this all looks very simple, but it's not. So how well does it work? Here is the prediction from the simulations. This is all for dark matter. This is linear theory. These are simulations, the blue points, and the green line is this prediction from the one loop standard perturbation theory. And you can see standard perturbation theory does do something right here initially, around k of 0.1, but then it quickly overshoots the simulations. All right, it's easy to understand why this is so. It turns out these are loop integrals. These loop integrals extend all the way to high momenta, to high Q. And because of that, you know, you go into a regime where perturbation theory is not supposed to work because density perturbation is larger than 1. And because of that, you should not trust the results in this high Q. So that's one reason, but there's an even more important reason, which is that perturbation theory in general should not work. Okay, I'll get to that in a second. You can also see, for example, that standard perturbation theory should fail for certain power law universes where the integrals just diverge, and whereas the real result, of course, doesn't diverge. Okay, so before I go to explaining what is missing in perturbation theory, let me tell you another way to do perturbation theory, which is using so-called Lagrangian perturbation theory. In this case, what we think about is not in terms of these fluid descriptions like density and velocity, but we think in terms of just particle displacements. So we write the particle position as the initial position plus the displacement. Okay? And then we can get the density perturbation by just mapping from the initial density, which is homogeneous, to the final density. Right? So we get this kind of Jacobian, which, for example, you know, if you know what psi is, you can do its gradient here, and you can write this kind of solution, which is called the so-called Zeldovich approximation. It turns out that you can write perturbation theory this way in this formalism as well. You get an equation which is an equation for this displacement field rather than for the density. It's a single equation, but of course displacement field is a vector. And the equation looks like this. You can again plug in perturbative ansatz and get a hierarchy of solutions, of which the first one is just the so-called Zeldovich approximation. Essentially it's like linear theory, except it goes beyond linear in the sense that you can get very high densities, and you can even get caustics and so on in this case. This is so-called 2LPT solution and so on and so forth. Okay, so very similar. So how well does this one work? This one has the opposite problem. Here again, I'm showing the ratio of the power spectrum to the basically so-called no-wiggle linear power spectrum. This is the linear theory, this line here. These are the simulations here. This is this SPT1 loop that I've shown you before. And then these are the various LPT solutions. And these have the problem, Lagrangian perturbation theory has the problem of not having enough power. So it's the opposite problem of SPT. But on the other hand, Lagrangian perturbation theory does something's right. For example, it gets the Baryonic acoustic oscillations very, very well. This is linear theory. Okay, SPT doesn't do so well in this regime. But Lagrangian perturbation theory, for example, just a simple Zeldovich does really well on explaining the damping of the Baryonic acoustic oscillations. Okay, so let me move on. So if we look at the pictures of the simulations of LPT, we can understand better what's failing in LPT. And what is failing is that LPT, Lagrangian perturbation theory, doesn't condense particles into dark matter halos. This is the true simulation, which you can see all these dark matter particles inside these clumps called halos, whereas LPT doesn't do that. Okay, so why doesn't it do that? It doesn't do that because it doesn't stop particles at the shell crossings. Okay, the particles just keep streaming. In the Zeldovich approximation, that's obvious. You know, it's just particles just do this, create a caustic, and then just keep moving on. In fact, it's a nice way to see this in 1D, which I think is useful. In 1D, the reason why it's useful is because in 1D, if you write down the dynamics, you can write down an exact solution in perturbative sense. And the reason for that is that force is dependent on distance, so you can actually exactly solve. And it turns out this one LPT, Zeldovich, is actually not an approximation, it's an exact solution in perturbative sense. You can also show that SPT, the one that I've talked about before, SPT, if you resum SPT to infinite order, you will get LPT, one LPT. So in this sense, SPT is inferior to one LPT in 1D because it is always, only in infinite number of loops you get to LPT in this case, in 1D. However, neither of these are correct. And the reason they're not correct is because of the shell crossings. Here I'm showing you, for example, so there's several lines here. There's, for example, second order SPT, which you see it always differs from the full nonlinear, which is blue. But Zeldovich, which is red, initially is perfect against the blue. It's still perfect here. This is a function of time. And then once you have the shell crossings, what happens to the dark matter is that it sticks together. It's glued together inside these shell crossings, which we call halos. And whereas the Zeldovich just keeps streaming through and creates an error, which you can see, for example, here. Red is not different from blue. Okay, so this shell crossing happens shortly after the perturbations go nonlinear. So one way to think about this is that the reach of SPT is roughly where things are nonlinear, so roughly where dense perturbations are Fourier unity, whereas the reach of PT itself is roughly where things collapse, which, for example, in 3D, we know things collapse roughly at the order density of 1.68 or so. So it's going to be on slightly smaller scales, but not much different. All right, so convergence radius is larger for the non-perturbative effects, but they are still of the same order. Okay, so what about the power spectrum in 1D? Power spectrum in 1D is shown here. For example, this is now Zeldovich power spectrum, which I've said is exact at the perturbative level, and this is the black line here. But the true power spectrum from the simulation is this one here, and clearly they differ a lot. Okay, and they differ by so whatever the difference is between these two is non-perturbative. It's something beyond perturbation theory. So what can we do in that case? Well, obviously we cannot use perturbation theory anymore, and so the best thing we can do, we can just parameterize our ignorance, and we can do this by either adding something to the perturbative solution or taking the ratio. Right? So these are simple ways. So for example, if you take the ratio, we call this ratio the transfer function, and we can expand this transfer function in terms of simple expansions. For example, it turns out that because of the mass momentum conservation, the lowest order expansion term has to go as k squared, and then there may be other terms. Okay, so this is basically what effective field theory does, more or less. It's basically you can parameterize this and assume that maybe this coefficient there's just one coefficient, it's k squared, or maybe you add more coefficients. Here, in fact, I'm showing you how well we can do using this ansatz as a function of these coefficients. For example, if you write this transfer function as 1 plus ak squared, then that gives you 1% accuracy up to k of 0.2 roughly. Then if you go to third order, then it gives you 1% accuracy up to k of 0.5. But again, these are things, where do things go nonlinear? They roughly go nonlinear here. And for example, if you do the SPT, look at the SPT expansion, which I told you that adding SPT adds up to Zeldovich, then one loop SPT fails already at k of 0.05. Two loop SPT fails roughly at k of 0.1. This is this one here. And then even 5-loop SPT doesn't do much better. Okay, so the two have similar radius of convergence, but the failure of PT itself has slightly larger radius of convergence. So you can get pretty far by just assuming the first order expansion. All right, so what happens? So which of these lessons can be then expanded to 3D? Most of these things are still true in 3D, except that it's no longer true that LPT is necessarily better than SPT. The reason for that is that in 3D you get these higher loop terms, both in SPT and LPT. They no longer can be shown to be a convergent series in the sense that, for example, in 1D, you can show that at low k, 2 loop stars at k to the 4 p linear, 1 loop at k squared, and so on. So there's a convergent series at low k. In 3D, this is no longer the case. And the reason for that is that there are basically additional terms that come in, additional displacements, that for 1 loop, for example, here I'm showing you just the ratio of the predictions of the 1 loop LPT against the 3-level LPT relative to the simulations. And as you go to low redshift, it's getting worse and worse. So there are additional contributions that are completely spurious. And they're spurious because particles should be glued inside the dark matter halos, and they're not in these approaches. Okay, so, and because of that, the high loop terms can be completely wrong, and it's not even clear that you gain much by adding them. So, so what are the challenges for broadband power? Then, well, you know, as I already mentioned, one challenge is, well, how do we know that we need just one parameter? Okay, fine, maybe it's good enough. But there's certainly more parameters that need to be included to cancel these higher loop terms, right? And so it's, you know, it's then technical challenge, basically how you do this and how many parameters you need to introduce and so on and so forth. So I won't go into details. There's also this issue of stochasticity. Basically, you know, the way I defined this was in terms of this transfer function, which in principle should really be cross correlation between perturbation theory and the full solution divided by the Euler correlation. And the difference between the cross correlation and whatever is left is called stochastic terms, and those are also important, and they become of order 1% roughly at k of 0.2. Anyway, so there's basically, so let me skip this and let me just show you, for example, one thing you can do is you can try, just look at how far you can do with perturbation theory and then parameterize your ignorance by introducing these so-called EFT parameters. And then you ask, well, how large are these EFT parameters and how much are they changing with scale? So we've done this here in this exercise. And for example, this is the Zeldovich approximation. And you can just define, you know, just like in 1D, you can define an EFT parameter relative to Zeldovich. And, you know, you get it, but it's changing with scale. Okay, so this is the dashed line here. You can do the same thing for various other perturbation theory approaches. For example, this one is for 1 loop SPT, which you can see it's roughly constant up to k.1, but then it's changing with scale again. And you can also do this for example, 2 loop SPT, which, you know, if you're optimistic, then you can say it's roughly constant here in this range, but then again, it's changing with scale here. So basically, these are the challenges that one needs to address if this is to work. And if you insist that this has to be a number, a constant number, then you can see that, you know, you can only go up to k of 0.2 or so, which is also where stochasticity becomes important. However, on the more optimistic, on the more positive note, this approach certainly helps in terms of explaining the residuals in the baryonic acoustic oscillations. Here I'm showing, for example, the residuals for various of these models, where I'm just asking how well do these models explain the damping of baryonic acoustic oscillations beyond their usual value. And you can see that some of these models do really, really well. In other words, they really explain all of the damping really well, you know, to precision, which is, you know, a fraction of a percent. So in this sense, it's very good. So how can we do better? How can we go to higher k? So phenomenologically, what we usually do is we introduce a so-called halo model. What went wrong in perturbation theory? Perturbation theory was unable to do small-scale halos, shell crossings. All right, and so what we can do is we can just add another component, which are the halos, which are basically the places where the shell crossings occurs, and we add their correlations both inside the halos, which we call the so-called one halo term, for example, and, you know, we can expand this one halo term in terms of the moments and so on, and we get this kind of expansion. And then there's also correlations between the halos, which we can also expand and so on, and we get terms like this. I won't go into details, but this approach, at least physically, phenomenologically, you know, allows you to go, you know, to much smaller scales. Of course, always at the price of introducing parameters, but that's all we can do, right? Remember, perturbation theory can only get you so far. You'll never be able to do shell crossing with perturbation theory. So we really just want to parameterize our ignorance in the best possible way. Okay, so for example, here I'm showing a total, an example of this, where the black solid line is a simulation, the blue line is a Deutsch power spectrum, and then I'm adding this one halo term here, and I get a total which agrees very well with the total, with the simulation. And here's another example of this, of this kind of modeling with 3 extra parameters, for example. You can get very, very precision up to high K, small scales. Okay, so, but nevertheless, this was just, to some extent, academic exercise because this was all dark matter, but the data really don't care about that so much because in the real world we observe galaxies. We also observe dark matter, but usually it's mixed with some other stuff. So let me just tell you quickly about real world in terms of galaxy clustering. We observe these things. We measure, for example, the amplitude of clustering power spectrum of normal galaxies or of these red galaxies. We go and we see that they are very different. So there's a, for example, there's a power spectrum of normal galaxies, there's a power spectrum of red galaxies. There's a factor of 4 difference here. The reason for that is that there's a biasing in there. Galaxies are not tracing dark matter perfectly. They are tracing the dark matter up to a constant, or maybe it's not even a constant, maybe it's a function of scale. And we call this bias. Okay, so how can we determine this bias? One way to do this is to use redshift space distortions, where the velocities that are basically in the radial direction, what we're measuring is not just the position of the galaxy, but also plus velocity. And so we can do this to measure redshift space distortions, as we call them. So the contours of eyes of constant correlation function become squashed like this. And the information of squashing is hidden in terms of velocity relative to density, which we call the so-called logarithmic growth rate, f. This is another picture of this, where I'm adding also the nonlinear effects. In terms of on small scales, we have virial velocities inside the halos, which produce these kind of distortions in the radial direction, and this is a completely nonlinear effect which we cannot model using perturbation theory. So then what do? Well, we try again. We try to combine the perturbation theory on large scales using some kind of this effective description on small scales. Here's the data where we see on large scales, the data look really good compared to these simple analytic models on large scales, but then on small scales we start seeing these so-called fingers of God here. Okay, if you take this and take the power spectrum, you get this kind of measurements. I don't have time to go into this. But basically, can we model the quasi-linear regime and extract more information? The answer is yes, but at the price of adding more parameters. And basically, these parameters, again, they are kind of halo model based, and they are trying to encompass all the ignorance and all the small scale phases that we have no hope of getting out of perturbation theory. Here is an example. Basically, we have tried this using modeling the power spectrum in simulations. Here's the power spectrum function of angle along the line of sight, and the message of this picture is twofold. First of all, linear theory would predict these lines to be flat. You see, they're never flat. In other words, nonlinear effects are extremely important to modeling redshift space distortions at all scales, pretty much, and so it's really, really important to include nonlinear effects. On the other hand, these models, the solid lines through the simulations, do a pretty good job. The residuals are 4 to 1% up to K of 0.4. And so there's hope that, using this nonlinear modeling, one can do a lot better. Okay, so I was going to mention also weak lensing, but I think you heard about this from previous talks, and especially Joe Dunkley probably has shown you this state-of-the-art in the weak lensing of cosmic accurate background. So let me skip this. Let me just mention one more thing, which is on small scales in weak lensing also, we don't measure just dark matter power spectrum in weak lensing. There are baryons that are affecting things inside the halos. And again, we want to basically immunize ourselves against that. We want to have a good description of how we get rid of those effects and still extract information. We can do this exactly the same way as we have done in all these other cases. For example, a halo model. In a halo model picture, we can say, well, the mass hasn't changed inside the halo, but it has been maybe redistributed because we have AGN feedback effects changing the mass distributions and so on, but not changing the mass. So this is a good way to describe this, and even though the effects are large, if you know how to describe them and you know how to marginalize over them, then you don't lose much information. So this is one message that's coming out of these things, that even though the effects appear large, they're not actually all that bad in the end, because we know how to marginalize over them. Okay, finally, just one application of all this machinery is neutrino mass. Why are we doing this large-scale structure? We want to measure a lot of things, neutrino mass and so on. Neutrino mass, what happens if neutrinos have mass, they suppress the structure on small scales relative to large scales. And this is something we can measure if we compare the large-scale structure observations like this to the CMB. You can see that the suppression depends on the amount of mass. So the more mass neutrinos have, the more the small-scale structure is suppressed. And we therefore observe galaxy clustering or recleansing, we can extract neutrino mass. The current state of the art of this is shown here. These are the large-scale structure constraints, and these are the CMB constraints from Planck, and they kind of combine here. This is now in omega matter and sigma 8 plane, which maybe you don't care about, but if you look at, for example, constraints on neutrino mass, then you're getting this kind of posteriors. This depends actually somewhat on this so-called optical depth. That is a complication in the case of CMB. So let's choose a value that has been recently advocated by Planck, and then we get the sum of neutrino masses is peaks at roughly 0.14 with roughly 2 sigma away from 0. So we're starting to see some evidence of non-zero neutrino mass, but we certainly are nowhere near to distinguishing between normal hierarchy and inverted hierarchy of neutrinos. Okay, another thing, this is my last slide well, next to last slide. And I just want to, I mean, probably you've heard this before from Joe Dunkley, but I just want to, leave you how impressive the recent combination of large-scale structure and Planck has been. If you take curvature is an important parameter, okay? The string theorists, for example, tell you that this is the most important parameter to go and measure. If you go and measure just from the CMB, you get an error which is of order 1% or so. By the time, then you add lensing, the error drops down by a factor of 3, and this is lensing of CMB, so this is still just Planck data. And if you add also then the BAO, really just Bose data, then it drops down by another factor of 4, so that overall, adding basically lensing and BAO to Planck reduced the error on curvature by a factor of 12. This all happened basically within last few months. Right, this improvement by factor of 12. So it doesn't very often happen that you get a new experiment, at least in cosmology, where things improve by a factor of 10 or more, and yet the value is still consistent with 0. Right. So no open universe and no confirmation of, or this confirmation of landscape yet. But nevertheless, we can do a lot better in the future. There's going to be a lot of surveys in this future, both spectroscopic surveys called DES, EPFS, and imaging surveys, DS, a lot of names. The plan here is to measure hundreds of millions of galaxies on the imaging side and tens of millions of galaxies on the spectroscopic side, and just get more and more information. There's also a lot of improvement on CMB, and there are also new techniques. All right, and so let me just show you one more slide, which is how well we may be able to do in the future with these surveys. For example, we can look for the running of the spectral index and try maybe to probe inflation using the running of the spectral index. And we can probably hope to do a lot better on the primordial negociality, which I have not talked about a lot. But future surveys of large-scale structure can do really, really well on the primordial negociality, maybe getting errors below 1 or maybe even below 0.2 or so. And with these kind of things, we can probe inflation really, really well with the future surveys. Okay, this is actually just a proposal of so-called spherex. It's not approved yet, but it's really exciting if one can realize this. Okay, so let me leave the summary here and stop.
Thank you very much. My question related to the stochastic term that you told us in the EFT theory. What do you mean about the stochastic term?
Yes. So let me answer this in the language I was using here, okay, and probably other people working on EFT maybe have a different definition. But in the language I was using here is that you can, for example, use your perturbation theory, like 1 LPT, 2 LPT, and then you can cross-correlate that with the dark matter. And you get something. You can then pull all the information that comes from the cross correlation, and there's still something left, all right, to the total power spectrum. And we call that something left, we call that stochasticity. The reason why we separate this is because we expect that at least at low k, that this correlated part goes as, for example, p linear times k square, whereas this uncorrelated part, this stochastic part, goes initially as k to the 4 due to the mass momentum conservation, and then does something else at higher k. But they have very different functional forms. One scales with p linear, the other one doesn't.
Okay. One more quick question. Urgent questions? No? Okay, so let's thank the speaker again.